Okay, so last time we talked about the Aldol reaction, in which we take an aldehyde and treat it with acid or base. Most examples of the Aldol reaction are base catalyzed, so that's what I'm going to typically use. And you end up getting the aldol product, which is a 3-hydroxycarbonyl. And this can also eliminate to form the aldol condensation product as well. If you do this with two different aldehydes present, you end up getting a mixture of them. Mixture of products where one's acting as the nucleophile, the other one's acting as the electrophile. Where you get also the self-condensation. And of course, each of these have multiple chiral centers, so there's much of this, plus the alkene products. To kind of start to clean up this a little bit, say you want just one of these products, say you want this product right here, what you need to do is use LDA. And again, LDA is that strong hindered base that allows you to designate that this molecule right here, that molecule is going to be our nucleophile. It does that by irreversibly deprotonating it first. Then you add in your electrophile, and it does the aldol reaction, followed by careful protonation, to give at least the constitutional isomer that you want. And this helps take out the risk of the alkene products as well, because you're very carefully controlling conditions so it doesn't overreact. Now, it is entirely possible to do these mixed aldol reactions with two different carbonyls without using LDA. In that case, you have to be very careful of which ones you choose. So this is an example of an aldol reaction that works quite well. Because this molecule right here is an aldehyde without enolizable protons. That means it can only act as an electrophile. And this right here is a ketone. It has an enolizable hydrogen. I'll just highlight that in blue. Meaning this is your nucleophile. Now in this reaction right here, you get the aldol product, but this is the minor product. Because the reaction is hard to stop. And this is the major product. The more conjugated the system, the more likely it will eliminate. What I mean by a conjugated system is you have essentially this pattern of double, single, double, single, double, single, double, single. All this conjugation, all of these atoms are sp2 hybridized. They all have p orbitals that are all adjacent to each other. And the more of these systems you have in play, the more stable the product is, therefore the harder it is to stop at the alcohol. Because the alcohol has an sp3 carbon that breaks up conjugation. But if you eliminate that alcohol, you get a nice, highly conjugated system. So, if the carbon attached to your electrophile is sp2, very likely you will end up with the condensation product. I.e. the elimination product. Not the 3-hydroxycarbonyl. Now, ketones tend to be more stable than aldehydes. and aldol reactions are reversible. So essentially, when you do an aldol reaction with an aldehyde, it's reversible. And typically the right side's favored. When it comes to a ketone though, since ketones are more stable than that, typically compounds like this have a tendency to split apart into two ketones. It is still possible to make this. Typically use LDA, or you can use barium hydroxide. This one's a trick. Barium hydroxide is insoluble in a lot of things, and so that's why it's used in this case. But we don't have to worry about that. But typically, these have a tendency to be unstable and they go backwards. The backwards aldol reaction is called a retroaldol. And it's basically the aldol in reverse, where you deprotonate the OH minus, OMe, and these electrons swing down and they kick the enolate off. Followed by protonation. Okay. And that's just the reverse of the aldol reaction. Now let's do the Claisen condensation. The Claisen condensation involves esters as nucleophiles. Now, to kind of recap, what you can do is you can take a carbonyl containing compound that has enolizable hydrogens and add LDA to it. LDA is a strong hindered base. It takes off the most acidic hydrogen if there is a tie. It goes for the less hindered. So the blue hydrogen and the red hydrogen, they both have pKa's roughly around 20. So they have near equal acidity. LDA will then go for the blue one because that's less hindered. And you get the enolate. And technically, though you don't need to draw this, I'm just drawing this right here, it's a lithium enolate. Why I'm doing it this way is I want to draw your attention to a parallel with another reaction that we've already done lots of, and that's the organolithium reaction. Where we treat an alkyl bromide with lithium metal, we get an organolithium, which is essentially a carbanion, just like the enolate is. It's a carbanion. Now, if you treat this with an aldehyde, we've seen the results of that. Yeah, let's just put up the results. Treat this with an aldehyde. And then reprotonate. And here we protonate. Okay. Do you see how these reactions are very similar to each other? And I really ought to get rid of that heading because this isn't the Claisen condensation. This is the Aldol reaction. Compared to organolithiums. Okay, same, very similar process. The Claisen condensation. We'll do this one. The difference between Claisen condensation and Aldol condensation is that Claisen condensation uses an ester as the electrophile. So you can make the enolates as your nucleophiles. Again, let's do the organolithium right along beside it. Now, if you treat an ester with an organolithium, no matter how much organolithium you add, it will always add twice to an ester. Let's kind of clean this up just a little bit. There's your ester. Now when you use an enolate, though, treat an ester, the product that you get is a 1,3-dicarbonyl. You only add once to an ester. So there is something different about the Claisen condensation than the organolithium. Keep in mind the organolithium mechanism is your nucleophile adds, electrons go up, and your electrons come back down and kick off the OMe, creating a ketone, and ketones are more reactive than esters. So the R- can add again. In the case of the Claisen condensation, you only get single addition. And here's the mechanism. You form the enolate by deprotonating. And then once you have your enolate, you add in your ester. Ester swings these electrons go up. This is just like the Aldol reaction. This step is reversible. So far, it's a lot like the organolithium. Now the next step is the O- swings its electrons down, kicks off the OMe, and you get your ketone. Now here is where the reaction differs. Is before another E-link can add to the ketone, something else happens. This hydrogen right here has a pKa not 20, but 10. It's much more acidic than the starting hydrogen with a pKa of 20. The reason it's more acidic is because it's between two carbonyls. And so when the base gets kicked off, it gets kicked off right next to the acidic proton, and this step right here is the fastest step in the entire reaction. Now, I drew the electrons going to the right. You could have also had the electrons go to the left. It doesn't matter because those are the same molecule. They're just resonance structures of each other. So it doesn't matter which direction you send the electrons up. But if you notice, there's quite a bit of electron density being shared between the two carbonyls. Because of this resonance, this is less reactive to nucleophiles than the ester is. And as a result, you don't get further addition. And then this waits around to add the H0 plus. And you protonate. And you get the dicarbonyl. If you protonated the oxygen, you get the enol. The enol, in most cases, is less stable than the carbonyl, and it becomes a carbonyl by tautomerization. Okay. You don't necessarily need to use LDA to do the Claisen condensation. You can use an alkoxide with that. But after the Claisen condensation, there's always this H3O plus step. That's there to protonate the enolate to give you the 1,3-dicarbonyl. Now, it's important in this reaction, if you're not using LDA, that if you have an ester in your product, that match your base and your solvent. Hydroxides should not be used in Claisen condensations. So, think about that statement as we do the mechanism of the above reaction. This hydrogen right here is an enolizable hydrogen, except instead of being next to a ketone or an aldehyde, it's next to an ester. These hydrogens have pKs roughly around 25. They are less acidic than ketones or aldehydes. What that means is this initial step right here is quite slow. Because alcohols have pKs of 15, they are barely strong enough, the alkoxides are barely strong enough to pull the H off. But they can do it, it just takes a while. And then once you have the enolate, it reacts with the ester. Okay. One mistake that students make is they think, oh, that's my product, I can stop. What you have to remember is that the Claisen condensation always goes too far. Because of this acidic proton. There is no stopping this step. It's the fastest step in the entire reaction. Once you form this, it deprotonates this. This is actually what's called the driving force of this reaction. We'll get to that in a bit. But this is the product between the sodium methoxide methanol step and the H3O plus step. This is what's protonated. Okay. So, there's quite a bit of things to talk about in this reaction. First, let's talk about why the base and the solvent should match your product ester. And that's because of this slow step right here. Say you use ethoxide. Yes, ethoxide can form the enolate, just like methoxide can. But there's something else. Another reaction that ethoxide can do. And that's add to the carbonyl. This reaction is quite reversible. This reaction is simply transesterification. This is a side reaction. That leads to byproducts. And so instead of just having your initial ester in the reaction, you have your initial ester, methyl ester, plus your ethyl ester there. Now all of these are competing and they give different products. If you have hydroxide, this is even worse. Because you end up with a carboxylic acid. And carboxylic acids in base deprotonates. And you get the carboxylate, which is unreactive. This is saponification. So transesterification and saponification can compete with the aldol, can compete with the Claisen condensation. So you have to be careful. Now, having your alkoxide match does not shut down the transesterification at all. This reaction still proceeds. But the difference is you're swapping out an OMe with an OMe. They're the same, so it doesn't matter. Okay. The products of Claisen condensations are 1,3-dicarbonyls with a hydrogen on carbon 2. That's how you can recognize a product of a 1,3-dicarbonyl of a Claisen condensation. Here's a 1,3-dicarbonyl. It has a hydrogen on 2, so this could be a Claisen condensation. Now, how to break it down? And predict the starting materials that this could come from. Like the Aldol breakdown, you break the 2,3 bond. Carbon 2 gets a hydrogen. So far, the first 2 steps are just like the Aldol. Where they differ is the 3rd step. Carbon 3 gets an OR group of some kind, like an OMe, an OET, or this could be actually a huge group. Nature uses proteins as the R group in this reaction. Okay. Now, keep in mind, with the Claisen condensation, you have 2 carbonyls. That means you have 2 different ways you can break down any Claisen. Now on exams, that kind of thing, you only have to show one way of doing it. But keep in mind that both ways are theoretically possible. You just have to number the carbonyls the opposite way. Okay, that's all we have time for. We will pick this up on Wednesday, especially when we're talking about this requirement here about there needing to be a hydrogen on carbon 2. If you don't have a hydrogen on carbon 2, that means that 1,3-dicarbonyl didn't come directly from a Claisen. And we'll talk about that on Wednesday.